This problem says that Scott needs $4,500 for a future project. He can invest $2,500 now, and he'll get an annual interest rate of 12.5%, compounded semi-annually. Assuming no withdrawals are made, how long will it take to have enough money for his project? Round your answer to the nearest hundredth. Okay, so this is obviously a compound interest problem, and the formula we have for compound interest is the amount. Let me change that to the blue that we're used to. So the amount in the account is going to be equal to the principal invested times 1 plus R over N, that is the rate over the number of times it compounds per year, times N, raised to the power of N times T, where T is how long the investment is kept in. So for this problem, we're told that P is equal to 2,500. That's how much he's investing. The interest rate is 12.5%, which always remember we have to convert that to a decimal before we can use it in our equations. And N, well, we're told that it's compounded semi-annually, so it's every 2 months. So N is going to be equal to 6. And T, well, T is something we don't know. T is what we're trying to solve for. But plugging all this in, we'll get an exponential growth function that looks like this. A is equal to 2,500 times 1 plus R is 0.125 over 6 raised to the power of 6t. In other words, A is going to be 2,500. And what I'm going to do is I'm going to just get a common denominator between these two fractions. The common denominator would be 6. And when I add all that up, I'm going to have 6.125 over 6 raised to the power of 6t. And the reason that I did the inside like that is I don't want to do any rounding until the very end. And so writing this as a function, the function we care about is A of t is equal to 2,500 times 6.125 over 6 to the power of 6t. So this function here is going to tell us how much Scott has in his account at time t. And he needs to know, well, how long does it take for that money to turn into $4,500 through the power of compound interest? In other words, what we need to do here is solve 4,500 equals 2,500 times 6.125 over 6 to the power of 6t. We need to solve this equation for t. Okay? Now, we have a variable in the exponent, and one of the ways that we can solve that is by graphing the original function a of t and graphing 4,500 and seeing where they intersect, and that'll tell us what t is. So again, to graph those two functions, the compound interest formula function and the constant function, 4,500, I'm going to use Desmos again to do that. So I'll define a function a of t to be 2,500 times the quantity of 6.125 divided by 6, and then all that is going to be raised to the power of 6 times t. Now, that is on my graph. We can't see it because of that 2,500 in the front, so we have to hold in shift and drag down the y-axis until the function shows up right there. And that is the graph of that compound interest formula function. And now we will graph another function, which will be the 4,500. So I'll just define f of t to be the horizontal line 4,500. And the point where those two functions intersect is what I'm interested in. I want to know when they're the same. And again on Desmos, when I click that line, or when I click a point where two functions are close to each other, it gives me the point of intersection. Now, that point right there is in the form t comma a of t. That is, it's a time and it's an amount. So remember what I'm trying to find out. I'm trying to find out how long will it take. That is, for what time, how long will it take for that money to grow into $4,500? Well, we see here that when t is 4.751, a of t is 4,500. Now, rounding that to the nearest hundredth is going to tell us that the solution we want is when t is equal to, rounded to the nearest hundredth, 4.75. That is how long it will take the $2,500 to grow into $4,500 if there's an interest rate of 12.5% compounded semi-annually.